magical constant C that works for all primes except for P. P can't be equal to 2. Let me write that down if this screen will cooperate. P not equal to 2. We'll check that out at the end of the video, but we're supposed to find a C such that the product of any prime C other than 2 the number of divisors is just equal to C. Okay, this is the counting function for divisors. Now, this is an important combinatorics result. I'm not even sure we need it. They'll come to think of it as the way this works out. What we do need to know is that by definition, D of any prime, the number of divisors, and this is literally the definition of a prime, is equal to 2. Okay, literally, if you define the divisor function first, you could define prime numbers this way. Okay, now, again, like for example, 7 has the divisor of 7 and 1, 13 has a divisor of 13 and 1, and so on. So it's clear this holds for all P. Now again, if P is not equal to 2, this function is what they call multiplicative. You can split it. So you can bring the D of P outside and it's equal to 2. Okay? And so what we get is this statement right here, which implies that C must be some multiple of M. So the only way I know to do this is just go through and check it out for the cases. If you do M equals 1, you get D at 2 is not equal to, what do we got there? Is not equal to C over 2, which would be a 1, right? Yeah. So it's not equal to 1, right? We know that D of 2 is 2, right? Again, y'all, just put the 2 right here. Now let's do M equals 2. And this is probably something a lot of you could just guess in the test. Now that's going to give rise to D of 4. But we know that that's equal to 3. You can just count them 1, 2, 3, right, of their divisors. That's equal to 3, but it's not equal to 2, right? Which is what this formula would predict, right? M equals 2 gives us C equals 4, right? And 4 over 2 is 2. So it doesn't work for the case for 2 and 4. Let's try 3. So M equals 3. That gives us what? D at 6. Now we do use this formula here, but you can just count them up. D at 6 is equal to 4. Okay, but it's not equal to, D at 6 is equal to 4, sorry. Right? 1, 2, 3, and 6. But that's not equal to 3. All right, let's try 4. M equals 4. Gives rise to D at 8. Now, again, you can count this. This is 2 cubed, which has 4 divisors. Also, you can just add them up. It's equal to, this is 2 cubed, and you can increment the exponent. So this is equal to 4. Okay, but that is what this, God, I keep doing that. That's equal to 4. Congruence is on the mind. But notice that is equal to 8 over 2. So we seem to have proved that our C has to equal to 8. Now this is something you probably could have guessed without going through all the formality, but let's just look at a couple of examples. D at 13 times 8. 13 is a prime, right? D at 13 times 8. Oh yeah, we are using that formula, aren't we? Now y'all, this is the same as 2 cubed. So you have 1, so you have this is equal to 2 times 4. Right? And you can just see that's true for every prime. Okay, then 2 cubed has 4 divisors, so you see it's always going to work. Always going to work. D at 31. I mean, it's really kind of silly to do this in a way because it's 31's a prime. Okay? Maybe I should write this a little better. This is equal to D at 31 since they're relatively prime. Times D at 8. This is a little more professional. Never been accused of being professional in my entire life. Okay, and this is equal to 2 times 4, which is equal to 8. But you see, that's just going to work out in the general case up here. You know, if you could almost guess this, I think, without going through everything I just did. If you write down D at P, and you can see what the problem is with 2, right? It just doesn't work out with 2 because they're not relatively prime and you can't take advantage of the multiplicative property, you know. But so if you have D at P times 2 cubed, which is what 8 is, right? And they're relatively prime, you get D at P. This is overkill, but just to be sure, times D at 2 cubed. Which is equal to 2 times 4. Equal 8. So there it is, folks. Your magical constant. Now, I'd like to know if there's any others like this. C is equal to 8. And again, you can verify that it does not work for 2. What would you get? 2 times 8 is 16. So you would get 5, not 8 back, right? 16 has 5 divisors, not 8. So it doesn't work for 2, but it works for all other primes.